grow up one day to be you, but is just starting to learn. For my part, I've now been preparing for this interview for several months. Including doing background conversations with many members of your team, but I'm not an engineer. So my goal is to help that audience see the future that you see. So I'm going to ask about 3 areas. The first is, how did we get here? What were the key insights that led to this big fundamental shift in computing that we're in now? The second is, what's actually happening right now? Well, how did those insights lead to the world that we're now living in that seems like so much is going on all at once? And the third is, what is the vision for what you see coming next? In order to talk about this big moment we're in with AI, I think we need to go back to video games in the 90s. At the time, I know game developers wanted to create more realistic-looking graphics, but the hardware couldn't keep up with all of that necessary math.
Not enough math.
NVIDIA came up with a solution that would change not just games, but computing itself. Could you take us back there and explain what was happening and what were the insights that led you and the NVIDIA team to create the first modern GPU?
So in the early 90s, when we first started the company, we observed that in a software program, inside it, there are just a few lines of code. Maybe 10% of the code does 99% of the processing. And that 99% of the processing could be done in parallel. However, the other 90% of the code has to be done sequentially. It turns out that the proper computer, the perfect computer, is one that could do sequential processing and parallel processing, not just one or the other. That was the big observation. And we set out to build a company to solve computer problems that normal computers can't. And that's really the beginning of NVIDIA.
My favorite visual of why a CPU versus a GPU really matters so much is a 15-year-old video on the NVIDIA YouTube channel, where the Mythbusters, they use a little robot shooting paintballs one by one to show solving problems one at a time, or sequential processing on a CPU. But then they roll out this huge robot that shoots all of the paintballs at once, doing smaller problems all at the same time, or parallel processing on a GPU.
3, 2, 1.
So NVIDIA unlocks all of this new power for video games. Why gaming first?
The video games requires parallel processing for processing 3D graphics. And we chose video games because, one, we loved the application. It's a simulation of virtual worlds, and who doesn't want to go to virtual worlds? And we had the good observation that video games has potential to be the largest market for entertainment ever. And it turned out to be true. And having it being a large market is important because the technology is complicated. And if we had a large market, our R&D budget could be large. We could create new technology. And that flywheel between technology and market and greater technology was really the flywheel that got NVIDIA to become one of the most important technology companies in the world. And it was all because of video games.
I've heard you say that GPUs were a time machine.
Yeah.
Could you tell me more about what you meant by that?
A GPU is like a time machine because it lets you see the future sooner. One of the most amazing things anybody's ever said to me was a quantum chemistry scientist. He said, Jensen, because of NVIDIA's work, I can do my life's work in my lifetime. That's time travel. He was able to do something that was beyond his lifetime, within his lifetime. And that's because we make applications run so much faster. And so you get to see the future. And so when you're doing weather prediction, for example, you're seeing the future. When you're doing a simulation, a virtual city with virtual traffic, and we're simulating our self-driving car through that virtual city, we're doing time travel.
So parallel processing takes off in gaming. And it's allowing us to create worlds in computers that we never could have before. And gaming is sort of this first incredible case of parallel processing unlocking a lot more power. And then, as you said, people begin to use that power across many different industries. The case of the quantum chemistry researcher. When I've heard you tell that story, it's that he was running molecular simulations in a way where it was much faster to run in parallel on NVIDIA GPUs even then than it was to run them on the supercomputer with the CPU that he had been using before.
Yeah, that's true.
So, oh my God, it's revolutionizing all of these other industries as well. It's beginning to change how we see what's possible with computers. And my understanding is that in the early 2000s, you see this and you realize that actually doing that is a little bit difficult because what that researcher had to do is he had to sort of trick the GPUs into thinking that his problem was a graphics problem.
That's exactly right. No, that's very good. Well,
So you did
some research.
So you create a way to make that a lot easier.
That's right.
Specifically, it's a platform called CUDA, which lets programmers tell the GPU what to do using programming languages that they already know, like C. And that's a big deal because it gives way more people easier access to all of this computing power. Could you explain what the vision was that led you to create CUDA?
Partly researchers discovering it, partly internal inspiration, and partly solving a problem. And a lot of interesting ideas come out of that soup. Some of it is aspiration and inspiration. Some of it is just desperation. And so in the case of CUDA, it was very much the same way. And probably the first external ideas of using our GPUs for parallel processing emerged out of some interesting work in medical imaging. A couple of researchers at Mass General were using it to do CT reconstruction. They were using our graphics processors for that reason, and it inspired us. Meanwhile, the problem that we're trying to solve inside our company has to do with the fact that when you're trying to create these virtual worlds for video games, you would like it to be beautiful, but also dynamic. Water should flow like water, and explosions should be like explosions. So there's particle physics you want to do, fluid dynamics you want to do, and that is much harder to do if your pipeline is only able to do computer graphics. And so we have a natural reason to want to do it in the market that we were serving. So researchers were also horsing around with using our GPUs for general purpose acceleration. And so there are multiple factors that were coming together in that soup. When the time came, and we decided to do something proper and create a CUDA as a result of that. Fundamentally, the reason why I was certain that CUDA was going to be successful, and we put the whole company behind it, was because fundamentally, our GPU was going to be the highest volume parallel processors built in the world because the market of video games was so large. And so this architecture has a good chance of reaching many people.
It has seemed to me like creating CUDA was this incredibly optimistic, huge if true thing to do, where you were saying, if we create a way for many more people to use much more computing power, they might create incredible things. And then, of course, it came true. They did. In 2012, a group of 3 researchers submits an entry to a famous competition where the goal is to create computer systems that could recognize images and label them with categories. And their entry just crushes the competition. It gets way fewer answers wrong. It was incredible. It blows everyone away. It's called AlexNet, and it's a kind of AI called a neural network. My understanding is one reason it was so good is that they used a huge amount of data to train that system. And they did it on NVIDIA GPUs. All of a sudden, GPUs weren't just a way to make computers faster and more efficient. They're becoming the engines of a whole new way of computing. We're moving from instructing computers with step-by-step directions to training computers to learn by showing them a huge number of examples. This moment in 2012 really kicked off this truly seismic shift that we're all seeing with AI right now. Could you describe what that moment was like from your perspective? And what did you see it would mean for all of our futures?
When you create something new like CUDA, if you build it, they might not come. And that's always the cynic's perspective. However, the optimist perspective would say, but if you don't build it, they can't come. And that's usually how we look at the world. We have to reason about intuitively why this would be very useful. And in fact, in 2012, Ilya Sutskever and Alex Krzyzewski and Jeff Hinton in the University of Toronto, the lab that they were at, they reached out to a GeForce GTX 580 because they learned about CUDA and that CUDA might be able to be used as a parallel processor for training AlexNet. And so our inspiration that GeForce could be the vehicle to bring out this parallel architecture into the world, and that researchers would somehow find it someday was a good strategy. It was a strategy based on hope, but it was also reasoned hope. The thing that really caught our attention was simultaneously we were trying to solve the computer vision problem inside the company, and we were trying to get CUDA to be a good computer vision processor. And we were frustrated by a whole bunch of early developments internally with respect to our computer vision effort and getting CUDA to be able to do it. And all of a sudden, we saw AlexNet, this new algorithm that is completely different than computer vision algorithms before it, take a giant leap in terms of capability for computer vision. And when we saw that, it was partly out of interest, but partly because we were struggling with something ourselves. And so we were highly interested to want to see it work. And so when we looked at AlexNet, we were inspired by that. But the big breakthrough, I would say, is when we saw AlexNet, we asked ourselves, how far can AlexNet go? If it can do this with computer vision, how far can it go? And if it could go to the limits of what we think it could go, the type of problems it could solve, what would it mean for the computer industry, and what would it mean for the computer architecture? And we rightfully reasoned that if machine learning, if deep learning architecture can scale, the vast majority of machine learning problems could be represented with deep neural networks. And the type of problems we could solve with machine learning is so vast that it has the potential of reshaping the computer industry altogether, and which prompted us to re-engineer the entire computing stack, which is where DGX came from, and this little baby DGX sitting here. All of this came from that observation that we ought to reinvent the entire computing stack layer by layer by layer. Computers, after 65 years since IBM System 360 introduced modern general purpose computing, we've reinvented computing as we know it.
To think about this as a whole story. So parallel processing reinvents modern gaming and revolutionizes an entire industry. Then that way of computing, that parallel processing, begins to be used across different industries. You invest in that by building CUDA. And then CUDA and the use of GPUs allows for a step change in neural networks and machine learning, and begins a sort of revolution that we're now seeing only increase in importance today.
All of a sudden, computer vision is solved. All of a sudden, speech recognition is solved. All of a sudden, language understanding is solved. These incredible problems associated with intelligence, one by one by one by one, where we had no solutions for in the past, desperate desire to have solutions for, all of a sudden, one after